Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchat, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first three: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested of course and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. Okay, so let's do this first one. So these examples, they were taken from the Ibler book, Statics, which is a book that is recommended for this model. So the idea of this example in this question 3.18 is to obtain the forces in the cables AC and AB. This system or this structure is holding this weight at point D of 20 kilograms, this ball. And you also have applied at point A this force, 300 newtons, F. So this is typically a problem of the equilibrium of a particle or equilibrium of a point. What we have to do is we have to basically isolate this point A. So I'm going to isolate this point A. Going to put it here, right? And then what I have to do is I just have to represent all the forces that are acting on this point A. We can start with the weight of the ball. So if I add the weight of the ball, I will have this force here, vertical direction, and the value of this force is equal to the mass of the ball, which is 20 kilograms, times the acceleration of gravity, right? Which I will consider 9.81, around 9.81, okay? This will give me the weight. Basically, it's the weight of the ball, which is the first force I'm considering at point A. Second force I will consider is this force F, 300 newtons. So it is this horizontal force here. So we know the value of this force. I'm just going to put here 300 newtons. Right? The units of the weight is going also to be newtons, of course. So we have the horizontal force F. What else do we need to include? We need to include the forces in the cables AC and BC, right? So let's start with cable AB. So we will have this force here. I will say this is my force F, AB. Vector here. Right? And the other force I have is the force in the other cable AC, which I need to include here. FAC. Okay? Right, so that's all the forces I have in point A, right? The other way you can also use to represent these forces is the idea here is to isolate point A, right? So you can imagine that, like if you have a scissor, right, and you are cutting the cables, cutting the cable that is holding the ball, and then when you cut the cable, you need to include the force in the cable, all right? Always like that. So in order to isolate point A, you need to cut all these cables, and then when you cut the cables, you are doing the free body diagram, And when you are cutting the cables, you need to include the forces in the cables, right? Which are internal forces in the cables. Okay, so these are all the forces we have in the cables. The only thing we need now to do is to write the equilibrium equations for a particle, right? And those equilibrium equations are summation of forces in the x direction equal to 0, summation of forces in the y direction equal to 0. Right? In a two-dimensional problem, this is what we have. Or if you want, you can do this in a different way. You can just add all the vectors. Right? So I'm going to use the red color to do in a different way. We are going to add all the vectors. So in order to add all the vectors, I need to have a coordinate system, right? We talked about this last Tuesday. So I'm going to consider this is my x direction, and this is my y direction, right? So we have our particle A, we have a coordinate system x, y in 2 dimensions in this case. This is a two-dimensional problem. And we have all the forces acting on point A. So this is the free body diagram of particle A. Now we can start adding all these vectors together. So I'm going to start with this 300 newtons. This force vector here, I'm going to add it here. So we have only a component in the horizontal x direction, agree with me? So this 300 newtons only has a component in the horizontal direction. So I'm going to write it 300, 0. Right? You all agree with me? This is the force F, the horizontal force F of 300 newtons. Second vector I'm going to consider is going to be this one, the weight. The weight. So the weight. So I'm going to add this weight vector. And this weight vector as a component in the y direction only. But it's going to be positive or negative? Negative, right? Is because the direction of this vector is opposite to the coordinate axis y. So I need to say x component of this force is 0, y component is minus 20 times 9.81. Right? Now we are going to work these other two forces, the forces in the cable, FAC and FAB. But before we do that, we need to decompose these forces into the coordinate axis. Right? We need to do that first. So all right, so we can obtain these angles here. They are not difficult. Before that, don't forget for this example 318, this distance d is equal to 1 meter, right? For the example we are doing, this distance is equal to 1 meter. So if I want to get, for example, this angle here, from here to here, how much is this angle? So we can use this figure here, right? So I have the vertical direction y, this one. I want this angle. So let's say this, if this is my angle alpha, tangent of alpha is equal to 2 meters over 2.5, right? So this means alpha is going to be the inverse of the tangent of 2 over 2.5. So alpha is going to be equal to, can someone please do this calculation for me? Yeah.
Is it alright if we take the angle on this side instead?
Yeah.
Yeah?
Yeah.
It's fine.
Yeah, it's perfectly fine. So you are saying if you take this angle, for example, right? This.
Yes.
Yes, it's perfectly fine. Anyone has this angle alpha, please? 38.66, right? So 38.66 degrees. Very good. So we can say that this angle here is 38.66. Now, for this other vector FAC, we will need this angle now. Now we can do in this way. This angle, for example, which means is this angle here, right? Let's say this is my angle beta, for example. So I can do a similar way. I can say tangent of beta is going to be equal to 1 meter over 2 meters. So it means beta is going to be equal to, sorry? 26.57 degrees, which is this angle here. I can put 26.57, okay? All right? So I'm going to clean this a little bit. So delete this. Okay. Now, let's start with force FAB. So I'm going to add my vector for the force FAB. So my x component, what I have to do is I have to decompose this force into an horizontal and a vertical component. I'm going to write like this. So this is my horizontal component, right? And this is going to be my vertical component, right? Can you see what I'm doing? So force FAB, I'm decomposing the force into the coordinate axis. Or horizontal one in the x direction. Basically, I'm projecting this vector into x and y, right? And now, for this vector here, we just add first the x component. You think is going to be positive or negative, the x component? Negative, right? So you can see why it is very important to decompose the force into the axis, because then you can see if it is positive and negative, and then you can obtain the component very easily. So as you said, the horizontal component is negative, minus, and what is the intensity of that component? So basically, I want this norm of this vector here. Yes? Minus FAB. So FAB is basically the intensity of that force FAB, right? We don't know yet. That's what we are looking for. You said times sine of let me zoom in. You all agree with this? For the horizontal component? What about the vertical component now? This component here, this one. What about this component now? You think it's positive or negative? Positive, right? So, and the norm of this vector is how much? FAB times what? Cos. Very good. So this is our force FAB decomposed into the coordinate axis. So the vector, force vector is here represented. Now let me see if I can do one thing. Let me move this a little bit. Yeah, I can move here. It's easier then. Now we need to add our final vector, which is our force FAC. So we are going to do the same thing for force FAC. So this can be a bit confusing now. Let me try to clean this up a little bit. So, with this. Oops. I think it's better to do it everything again, right? So we have our FAB that we did already, and we have our FAC. And this is our horizontal axis, and we saw that this angle here was 26.57, right? Is it correct? 26.57, right? Okay, so I also need the y-axis, is this one. So what I'm saying, what we have to do now for FAC is the same thing. I have to decompose this FAC into the horizontal and vertical direction. So this is going to be my horizontal component, and this is going to be my vertical component, right? So let's work the horizontal component first. It's going to be positive or negative? Negative. So we have FAC now, which is the norm of the force in the cable AC, and I need to multiply this by what? Cos 26.57, right? The vertical component, this one, is going to be positive or negative? Positive. And I have FAC, correct? Times what? Sine. Very good. That's all we have. You agree with me? This is all the forces we have. So now we just need to say that the summation of all these forces need to be equal to 0 to be in equilibrium. Or if you want, the resultant of the forces acting on particle A needs to be equal to 0. Is the equilibrium equation. Basically is the same as this condition that we have here. Doing that means I will have to say that the summation of these vectors needs to be equal to a vector which horizontal component is 0 and vertical component is also equal to 0. And when I now check the horizontal or x components of this addition of these vectors and equal it to 0, I have our first equation, which I'm going to write here below. Let's see. I can say, so what do I have? I have 300 minus FAB sine of 38.66 minus FAC cosine 26.57 needs to be equal to 0. This is my first equation, my first equilibrium equation. My second equilibrium equation, I need to look now at the vertical components of this resultant force, and then I can say it is equal to minus 20 times 9.81 plus FAB cosine 38.66 plus FAC sine 26.57 equal to 0. Right. So basically we have, now if you look carefully, we have two equations for two unknowns, which are FAB and FAC, which are the forces in the cables, AC and AB. So I just solve this system of equations and get the forces, get the answer for our question, all right? You see, if you do this kind of problems following this methodology, like creating the free body diagram, is extremely important. So this is the most critical thing, in my opinion, is the correct construction of the free body diagram. You have the body you are analyzing. In this case, is a particle. Particle A is our body. We isolated that body. By isolating, I mean we need to represent all the forces that were acting on that body, right? And these are all the forces that we had in particle A. And then the only thing we have to do now is to add all these forces together and say the resultant of these forces equal to 0 to be in equilibrium. And that will give us what we call the equilibrium equations. And if we have two unknowns, in this case the forces in cable AB, cable AC, we need two equilibrium equations to get these two unknowns, always like that. And this is a good